Hello and welcome to Padayon YouTube channel. This is for the class 10 and chapter 10. Refractions of light 10.3. Light seems to travel along the straight line path in the transparent medium. So if there is no obstacles between the light rays, then it will straight travel. But what happens when the light enters from one transparent medium to another? Does it still move along a straight line path or it's changed its direction? We shall recall some of our day-to-day experience. You might have observed that the bottom of the tank or a pond containing the water appear to be raised. So when you are in the swimming pool or somebody's swimming pool and you see the bottom of the swimming pool, it look raised. Similarly, when a thick glass slab is placed over some printed materials, the latter appear to raise when viewed through the glass slabs. So why does this happen? Have you seen a pencil when you put it partially immersed in the water in the glass tumbler? It appears to be a displace at the interface of air and water. So you might have observed that the lemon that you keep inside the water glass and tumbler, right? It looks bigger in the size than the actual size. So let us consider the case of apparent displacement of a pencil. Partly immersed in the water, the light reaching you from the portions of the pencil inside the water seems to come from different direction compared to the part of above the water. So this makes the pencil appear to be displaced at the interface. For a similar reason, a letter appear to be raised when seen through a glass slab placed over it. Does pencil appear to be displaced to the same extent if instead of the water we use a liquid like kerosene or turpentine? Will the latter appear to rise to the same height if we replace a glass slab with a transparent plastic slab? You will find that the extent of the effect is different from different pair of media. So the different medium has a different effect on refraction of the light. This observation indicates that the light does not travel in the same direction in all media. It appears that when traveling obliquely from one medium to another, the direction of propagation of light in the second medium changes. As in the simple word, you can say when light transfer from one medium to another medium, it reduces its speed or it increases the speed, but there is a change between two different medium. So this phenomenon is known as a refraction of light. So let us understand this phenomenon further by doing a few activities. So you can read the 10.7, 10.8. The coin becomes visible again on pouring water into the bowl. The coil appears slightly raised above its actual positions due to the refractions of light. In 10.9, and now let us look at the 10.3.1 refraction through the regular glass slab. So it's also a kind of an activity where the refractions of light through a glass slabs are done in 10.10. The steps of putting the glass slab and observing the refractions of a light. Now in this activity you will notice that the light ray has changed its directions from point O and O dash. Note that both these point O and O dash lie on the same surface, same plane, separating a two transparent medium. Draw a perpendicular and an N dash at AB at O and another perpendicular M and M dash to CD at O dash. The light ray at a point O has entered from a rarer medium to a denser medium. So that is from the air to glass. Now note that the light ray has a bend towards the normal at this point at O dash, and the light ray has entered from glass to air, that is from a denser medium to a rarer medium. The light here has a bent away from the normal. So compare the angle of incident and the angle of refraction at both refracting surface AB and CD. So in this figure 10.10, the EO is an incident ray and O dash is a refracted ray of O-H is the emergent ray. Now you may observe that the emergent ray is parallel to the direction of incident ray. So how does that happen? The extent of bending of the ray of light at a opposite parallel face, that is AB and CD, of the rectangular glass slab is equal and opposite, and this is why the ray emerge parallel to the incident ray. However, the light ray is shifted sideward slightly. What happens when the light ray is incident normally to the interface of two media? So you can try this out. Now you are familiar with the refractions of light. So refraction is due to a change in the speed of light as it enters from the one transparent medium to another. This experiment shows that refraction of light occurs according to the certain laws, and we all know very well about the two famous laws. The following are the two laws of the refractions of light: the incident ray, the refracted ray, and the normal to the interface of a two transparent media at the point of incident all lies in the same plane. They are all on the same plane. Second, the ratio of sine of angle of incidence to the sine of angle of refraction is a constant for the light of a given color and for the given pair of media. So this law is also known as a Snell's law of refraction. So they may be ask you explain the Snell's law of refractions. If I is the angle of incident and r is the angle of refraction, then sin I upon sin r is equal to constant. So this constant value is called the refractive index of the second medium with respect to the first. So let us study about the refractive index in some detail. Now you have already studied that are the rays of the light that travels obliquely from one transparent medium into the another will change its direction in the second medium. The extent of the change in a direction that take place in a given pair of media expressed in the term of refractive index. The constant appear on the right hand side in equation 10.4. So the refractive index can be linked to an important physical quantity, the relative speed of propagations of light in a different media. It turns out that light propagates with a different speed in a different media. Light travels fastest in the vacuum with the highest speed of 3 into 10 raised to 8 meter per second. In air, the speed of light is only marginally less compared to that in the vacuum. So it is reduced considerably in the glass or water. The value of a refractive index for a given pair of media depends upon the speed of light in the two media as given below. So consider a ray of light traveling from medium 1 into the medium 2 as shown in the figure. Let V1 be the speed of the light in the medium 1 and V2 be the speed of the light in medium 2. The refractive index upon medium 2 with respect to medium 1 is given by the ratio the speed of light in the medium 1 and the speed of light in medium 2, and this is usually represented by symbol N21. So this can be expressed in an equation like speed of light in one medium divided by speed light in the medium 2. So by the same argument, the refractive index of medium 1 respect of medium 2 is represented an N12 and is given by N12 is equal to speed of light in medium 2 divided by speed of light in medium 1. So if the 1 is a vacuum of the air, the refractive index of the medium 2 is considered with respect to vacuum. So this is called the absolute refractive index of medium. It is simply represented by N2. If c is the speed of light, then the light in the air is v is the speed of light at the medium. Then the refractive index medium Nm is equal to by given by speed of light in air divided speed of light in the medium. So c upon v. So the absolute refractive index of the medium is simply called a refractive index. The refractive index of the several media is given in table 10.3. From the table you can learn that about the refractive index of water, that's 1.33. This means that the ratio of the speed of light in the air and the speed of light in the water is equal to 1.33. Similarly, the refractive index of the ground glass is 1.52, and such data are helpful to many places. They said, however, you do not have to memorize, but as long as you are in the 10th standard and this is given in the book, so you must try to remember, not from the table 10.3, that is an optical denser medium may not be possess a greater mass and density. For example, kerosene is heavier, higher refractive index, is optical denser than the water, although its mass density is less than the water. So that's the end of this point.